Hello learners, today we will discuss about the diversification of magma. This topic pertains to the course Petrology and the course code is BGYCT 135. Firstly, we will discuss about Bowen's reaction series. This will be followed by continuous and discontinuous series. Then we will discuss about the importance or significance of Bowen's reaction series, followed by diversification of magma, magmatic differentiation processes like assimilation and magma mixing, and finally we will summarize. In the earlier video, we discussed about the physical properties of the magma. Now, you will get acquainted with the processes of diversification of magma in this video. Now, let us define magmatic diversification or magma diversification or magmatic differentiation. This is the process by which single or homogeneous magma evolves into two or more fractions of different composition, ultimately forming diverse rock types. Before we initiate the discussion, let us get acquainted with Bowen's reaction series. It is also known as Bowen's reaction principle. Bowen's reaction series, what is it? Geologists, they have identified different types of igneous rocks based on the basis of intensive field investigation and petrographic study. We have already discussed this in the earlier video. So the study of genetic aspects of igneous rocks is known as petrogenesis. Research on genetic aspects of rocks led to think in terms of evolution of igneous rocks, which marked the turning point in petrology from petrographic approach to petrogenetic approach. Dr. N.L. Bowen in 1922, he enunciated the Bowen's reaction series or principle which developed the fundamental ideas of magma, their trend of evolution and origin. This sequence of crystallization is also known as Bowen's reaction series or Bowen's reaction principle. In this series, the minerals are so arranged that each is supposed to react with the magmatic fluid so as to produce the new mineral placed below it. We will discuss further. Bowen's reaction series, it illustrates how many magmas. Bowen's reaction series illustrates how many magma may solidify as a single rock type, or it may give rise to many rock types. Now, on your screens, you see Bowen's reaction series. You see, on your left, it is discontinuous series. Magnesium olivine is giving rise to iron olivine. And when iron olivine crystallizes, after that, from the melt, it crystallizes magnesium pyroxene, and then further iron pyroxene, and further amphibole, that is hornblende, and further biotite. So you see that there are different types of minerals that are crystallizing in the discontinuous series. With the decreasing temperature, the silica oxide content in the liquid is increasing. Whereas on your right side, you see calcium-rich plagioclase, and finally crystallizes sodium-rich plagioclase. This is known as continuous series because in this series, all the plagioclase minerals from anorthite to albite, you have minerals like bitonite, labradorite, they are crystallizing in between with varying calcium and sodium percentages. So initially when the magma, it undergoes cooling and crystallization, the resulting rocks are mafic. So now you see, as magma cools and crystallizes with the decreasing temperatures and increasing silica oxide content in the liquid, how the rock types they range. On your extreme right, you can see initially the single magma, when it undergoes cooling crystallization, it may form ultramafics with low silica percentage. Then further, with decreasing temperature, it can give rise to basalts and gabbro, that is mafic in composition. And with further decrease in temperature, andesites or diorites, they form, which are intermediate in composition. And finally, when with the decreasing temperature or the silica percentage increases in the liquids, it gives rise to rhyolites and granites, which are felsic in composition. Hope you understand this. So, a single parental magma, because of variation in physical conditions, it gives rise to different types of minerals crystallize, and it gives rise to different types of rocks of varying composition. This is known as Boffin's reaction series or Boffin's reaction principle. So let us elaborately discuss what are discontinuous and continuous series. In the previous slide, we had discussed that on your left, it was discontinuous series that comprised of different minerals, and on your right, it was continuous series which comprised plagioclase mineral with varying calcium and sodium percentage. So in this series, the minerals are so arranged that each is supposed to react with the magmatic fluid so as to produce a new mineral placed below it. Let me go to the previous slide. Now you see, magnesium olivine that undergoes reaction with the melt to form iron olivine. Then subsequently, iron olivine, it undergoes reaction with the melt to form magnesium pyroxene, and so on, so forth. Further we move. So, Boffin's reaction series illustrates how magma may solidify as a single rock type, or it may give rise to many rock types. On the left, as I told, it is discontinuous series, whereas on the right, it is continuous series. These two series, discontinuous and continuous, they converge and they merge into single series, which also forms the part of discontinuous series. So on your left, it is discontinuous series, which represents transformation of structure and composition of ferromagnesian minerals with decreasing temperatures, whereas on the right, it is continuous series, which represents cooling and crystallization of minerals of plagioclase series with decreasing temperatures. So in the continuous reaction series, as the name suggests, the mineral continuously reacts with the magma, forming the next mineral in plagioclase series. On the contrary, the discontinuous reaction series, the new minerals are formed when the magma reacts with the earlier formed minerals at a particular temperature. The minerals in the Boffin reaction series indicate a generalized order in which each mineral crystallizes from cooling basaltic magma. Unless the earlier formed crystals are removed from the melt, its composition will keep on changing further. After the early formed crystals are removed, the reaction between the magma and the crystal formed takes place to produce a new mineral. Hope you understand this. That unless and until the earlier formed crystal, suppose magnesium olivine, they are removed from the melt, its composition can be changed further. So the temperature range of Bowen reaction series is from 1100 degrees centigrade to 573 degrees centigrade. So the crystallization of silicate minerals, they begin at the temperature of minerals of spinel group, and that temperature is 1100 degrees centigrade. Spinel, that is magnesium aluminum oxide, is an oxide group mineral with cubic symmetry. They often occur as octahedral crystals. Discontinuous series. First mineral to crystallize in discontinuous series is Mg-rich olivine. It is followed by Fe-rich olivine. As soon as olivine is formed, unless and until it is removed from the crystallization site, it reacts with the magma so as to produce next mineral in series. Thus, with the following temperature, Mg-rich olivine, that is Mg-rich olivine is known as mineral phosphorite. It is converted to Fe-rich olivine, that is mineral phyllite. This continues further till the whole olivine is converted to Mg pyroxene under ideal physico-chemical conditions. I hope you understand this concept. As the crystallization of magma proceeds, there is tendency for equilibrium to be maintained between solid and liquid phases. Thus, the early formed crystals react with liquid and changes in composition takes place in order to maintain this equilibrium. So these two minerals, they are called as reaction pair. For example, Mg pyroxene, after reacting with the remaining magma, it is converted to Fe pyroxene and then to hornblende, and then further it gets transformed to biotite with the following temperature. Here again you see what I have explained to you. With falling temperature, you get more felsic composition of magmas. Left you have discontinuous series and right you have continuous series. On left you see the composition of magma is continuously changing. Continuous series. This series consists of plagioclase minerals which begin crystallizing more or less simultaneously with olivine. On one side, olivine is crystallizing. On the other side, you have plagioclase mineral crystallizing. So the first formed plagioclase crystals are rich in calcium. As the reaction goes on, the temperature drops and the crystals become progressively more sodic. This is well recorded in zoned plagioclase. You get zoned plagioclase, you get zoning in plagioclase. So this continuously changing composition is recording in zoned plagioclase, in which the core is calcic and it is surrounded by more sodic zones. Now what are doliomorphic rocks? Sometimes there is partial failure of reaction between olivine and the melt or magma. So this results in the enrichment of silica in the liquid. So the final crystallized product may be the mixture of olivine, pyroxene and quartz. Otherwise, see, when you get olivine, you don't get quartz as a free mineral, but during the partial failure of the reaction, you may get olivine with quartz. In this case, the quartz is known as release mineral and the rocks containing the release minerals are known as doliomorphic rocks. Thus, the doliomorphic rocks, they contain release minerals due to incomplete reaction or relics of early formed minerals which has escaped the reaction. Let us discuss the importance or significance of Bowen's reaction series. See, it establishes the process of differentiation and diversification of magma. It illustrates that a magma may solidify as a single rock type or may give rise to many rock types. The primary basaltic magma may solidify it as gabbro, diorite, granodiorite to granite, depending upon the degree of fractionation and the extent of removal of early formed crystal for further reaction with the melt. The silicate structure becomes more and more complicated from early formed minerals like olivine to the minerals like quartz. Early formed minerals, you see that they are more rich in magnesium and iron as compared to later minerals or late formed minerals in the Bowen reaction series. Now let us talk about the processes that govern the diversification of magma. So there are two main reasons for the origin of diverse igneous rocks: magmatic diversification and assimilation. We have discussed about the definition of magmatic differentiation in the earlier video. Now, what is magmatic differentiation? Again, we will discuss about magmatic differentiation. Magmatic differentiation may be defined as a process operating within the magma. This involves solid, liquid, and gaseous phase by which a homogeneous parent magma, it breaks into fractions with diverse composition and forms different rock types. The process of differentiation is concerned only with the variation which have clearly risen within original uniform body of magma, but not with the heterogeneity produced within the igneous mass by successive intrusion of different magma or by assimilation of rock material. I hope this is clear to you. This process of diversification is considered when from uniform body of magma you get different rock types. So the magmatic differentiation may be effective when the magma is in fluid state or in liquid, or it can be liquid and vapor system. Magmatic differentiation, there are important mechanisms or in processes of magmatic differentiation when magma can be in fluid state or solid mineral phases can be involved. In other words, magmatic differentiation can take place when the magma is in fluid form or liquid form or solid mineral phases are there. In fluid state, let us discuss the different processes. The first process in fluid state is liquid immiscibility. This means when a mixture of two different components, initially homogeneous at a particular temperature, but with the falling temperature, it may become immiscible and separate as droplets or bubbles from each other because of the difference in specific gravity. The phenomena of liquid immiscibility explains the presence of sulfides in silicate magma. The second process in fluid state that governs magmatic differentiation is liquid fractionation. This process has been considered as an important and effective mechanism by petrologists in which the differentiation of homogeneous magma can take place. In case of thermal gradient, the compound with which the solution is nearly saturated tends to accumulate in the cooler horizons. The gravitational diffusion takes place, separation and stratification of element at a homogeneous magma under the influence of gravity. So, the influence of gravity is primarily the factor that governs the diversification of magma in fluid state in case of liquid fractionation, whereas we discussed earlier about the difference in temperature that gives rise to liquid immiscibility. Now, the third process that governs diversification of magma in fluid state is the movement of volatiles. You know, volatiles are excellent solvents. They are capable of making selective transfer of materials from lower to higher levels. Thus, this develops when the volatiles are removed, it develops inhomogeneity in magma. We have read in the earlier video that the release of pressure and volatile tend to migrate towards the area of least pressure and distillation takes place. Now, let us discuss the processes in which the solid mineral phases are involved. So, in this process, fractional crystallization takes place when solid mineral phases are involved. What is fractional crystallization? With cooling and solidification of magma, the crystallization of minerals begin. It may be localized at margin where the cooling is faster. The cooling is faster at the margins and the temperature is lower in the margins, and in the central part the temperature is higher. So by the action of diffusion, the mineral formed during the earlier crystallization may be concentrated towards the margin of the igneous body, and the core of the igneous body can be more felsic as compared to the margin, which is more mafic due to crystallization and differentiation. So during the crystallization, there is a tendency for equilibrium to be maintained between the solid and liquid phases of the magma that we have read in Bowen's reaction series. So in order to maintain equilibrium between the early formed crystals, the reaction with the liquid takes place, and this changes the composition of the magma. So in Bowen's reaction principle, we have seen how primary basaltic magma may solidify and gives rise to gabbro. This may give rise to a rock varying through dunite, gabbro, diorite, granodiorite, granite, depending upon the degree of crystal fractionation and extent to which early mineral are formed and removed from the magma or the melt. Gravity settling. In crystal fractionation, gravity settling is an important phenomena which involves the sinking and floating of or suspension of early formed crystal within the magma. Monomineralic rock like dunite, pyroxenite, anorthosite are formed by this process, which cause gravitational shrinking, and monomineralic rocks are formed. So the rocks formed by the accumulation of these crystals are described as cumulates. So the separation and accumulation of crystals that changes the composition of the magma, this gives rise to evolution and diversification of magma. You see here early formed crystals, how they are settling in the magma chamber and the floor of the chamber. Filter pressing. In this mechanism, mechanical separation of the coexisting magma from the crystal mesh takes place, and as the crystallization continues, a loose mesh or framework of crystal with a residual liquid is formed. And at this stage, if the deformation takes place, the residual liquid will be squeezed, leaving behind the early formed crystals, and this phenomena is known as filter pressing. Now here you can see filter pressing. The earlier formed crystals are moved from the crystallizing magma. You can see on your right. Flowage of magma. When the fluid moves along the pipe or a narrow channel, flowage behavior at the center and away from the contact wall is different. We have already discussed, and this can result in the preferential accumulation of early formed magma. And again, crystal zoning, we have already discussed. If the equilibrium during the crystallization is disturbed, the successive liquids and the corresponding zones will have different composition, like you can get calcic plagioclase, which is successively rimmed by more sodic varieties. Assimilation is the process by which foreign rock masses are incorporated by the magma. It is also very important in bringing about the diversification of igneous rock. It also includes mingling of two liquid magmas, magma mixing, and these processes involve remixing of rocks with magma and result in heterogeneity and diversification of magma. Assimilation process is also governed by laws of Bowen reaction principle. Reaction can also take place with the magma and the host rock or the country rock. Assimilation or incorporation of foreign rock matter, it occurs by mechanical incorporation without chemical reaction, reaction involving partial solution of incorporated matter and solid phase, total dissolution, and reaction involving disappearance of solid phase. So these are the three mechanisms by which assimilation can take place. And the factors affecting assimilation are temperature at the time of intrusion, presence or absence of notable degree of superheat, composition of xenolith or inclusion, concentration of volatiles in the magma, conditions which facilitate or retard the escape of volatiles into country or surrounding rocks. You can see here the process of magmatic assimilation, wherein the host rock is getting assimilated or it is getting melted slowly in the magma chamber. Magma mixing can take place when two or more magma of different chemical composition, they come in contact with each other on the surface of the earth, and they produce composition intermediate between the two end members. If, for example, magmas are very contrasting, rhyolite or basalt, it can give rise to a composition of intermediate magma. You can see two co-mingling magmas, and you can see an outcrop wherein co-mingling of magmas is shown. Now, learners, let us summarize what we have learned in this video. We have learned about Bowen's reaction principle, which illustrates the differentiation and diversification of magma. It displays the crystallization of mineral in continuous and discontinuous series with decreasing temperature varying between 573 degrees centigrade to 1100 degrees centigrade. And we have also learned how magmatic differentiation by different processes can give rise to diverse composition and different rock types. We have learned about the different mechanisms like liquid immiscibility, liquid fractionation, movement of volatiles, fractional crystallization, gravity settling, filter pressing, flowage of magma, and crystal zoning. Lastly, we discussed about assimilation, which is the process by which rock masses are incorporated by the magma, and it includes mixing of magma too. I hope you enjoyed the discussion. Thank you.